Hello everyone, welcome to another video. Today we're going to be looking at, well, call it families of curves, but really there's sort of a few sort of things that we're going to sort of look at today. It's the graphs of functions versus their derivative and versus the antiderivative, etc., etc. So just looking at a few situations here. I'm not going to sort of talk about anything. I'm just going to get straight into an example and then you'll sort of see where we're getting at. Okay, so let's have a look at this. So if the derivative function f dash of x is equal to 2 sine 2x, we need to sketch the family of curves, and you'll see what I mean in a second, for y equals f of x. So we've got the derivative, but we want to sketch the function for the straight function f of x. Okay, so we'll do that first. The second thing we want to do is hence find the rule for f of x if it passes through. So then it gives us a particular point, but that won't make sense necessarily yet. So let's have a look first at what this is doing. So f of x, funnily enough, will be the integral or antiderivative of 2 sine 2x dx. Okay, so because we're told the derivative, so to find the function itself, we need to find the antiderivative. Okay, so that's equal to 2 sits out the front, sine goes to negative cos, so it's going to be, I'll just put a bracket there, negative cos 2x, and then we need to divide by 2 as well. So just divide by 2 out the front, plus c. Okay, we'll just double check that. I always like to double check after I do an integral. So the 2 is sitting out the front, 2 sitting out the front, sine goes to negative cos. That's why we've got the negative cos there. The 2x stays as it is, but then we need to divide by 2, and so that's where that 2 came from. All good, plus c. Okay, I'll just simplify this a little bit, and I'll just try to jam it up the top line here. So that's negative cos 2x plus c. All right, so that's our function. Now let's have a think about what this looks like. I'll just draw a graph here. Let's have a think about what that looks like. All right, so if c is equal to 0, let's have a think about what that looks like. I'll do it in green. If we've got negative, if c is equal to 0, then we've got negative cos 2x. What does that graph look like? Well, cos starts up at 1 and comes down like that. All right, so it goes from 1 to negative 1 like that. All right, negative cos x, therefore, is that's upside down. So it looks like this. So it comes up here and goes like that. All right, so I'll draw a few more sort of cycles like that. So from 1 to negative 1. So that's negative cos. Negative cos x would have a period of 2 pi, but because of that 2x, this will have a period of pi. And so what that means is from there to there, so that will be pi there, and halfway, so that'll be sort of pi onto there. All right, so just a couple of things there. So that there, this is a bit messy. That's okay. I just want you to get the idea. And halfway, negative pi on 2. All right, so that's what the graph would look like if, and I'll just put it in black, or just black. That's if c is equal to 0. That's what the function looks like. Okay. What about if c was equal to 1? Right? If c was equal to 1, and I probably should have given myself a bit more space. I'll do it in blue. If c was equal to 1, what would happen to that? Well, that c there, that c, that will lift the graph up by 1. All right, so if c is equal to 1, everything just moves up by 1. So it'll be here, and sort of come up like that, and it'll come down like that, and it'll come up like this, etc., etc. So that's what it would look like if c was equal to 1. Okay, how about if c is equal to negative 1? I think you might be getting the picture about here. C is equal to negative 1. That'll drop that green graph down by 1. And so it'll come down by negative 2, and it'll come up like this. I haven't drawn it very well, but hopefully you get the idea. It should actually hit on. Yeah, that should have actually hit there. You get the idea, and so that's what the graph would look like. I've drawn that terrible. If c is equal to negative 1. And so what you'll see here is that the solutions to this, so in other words, the f of x is here, the original function, because it's plus c, that plus c just moves that graph up and down. Okay, so you get the c is moving, that plus c moves the graph up and down. And it could be any of those graphs. It could be anything in between those graphs. It could be this. Well, I should have scribbled on. But you can see it just moves the graphs up and down. So that original solution, that general solution, function just goes up and down. And so that's an example of sketching the family of curves. So they keep on going up and they keep on going down. They don't move left and right, they just move up and down because of that plus c. Hopefully that makes sense. Okay, so that's part B. We've sketched the family of curves there, and so when you're asked to do that, you'll never be asked to do it in an exam, to be honest. But that's just what it means, just to have a draw on a couple. But maybe in an exam they'll show you that here's a family of curves, and they might say choose one, blah blah blah. But that's sort of what it looks like. B, hence find the rule for f of x if it passes through. Right, so they've given us a point now, right? So we know that there's a point, and if I just draw a point, let's just assume that that was the point. We know that our graph that we want, our original function, goes through a certain point. And so what we need to do now is solve for c. And so we're going to substitute that value back in. So I'm just going to write that down. So sub pi on 6 half into f of x equals negative cos 2x plus c, and we'll be able to solve what c is equal to, and then we'll get our function. Okay, so here we go. So therefore f of x, what is f of x? F of x, so half is equal to negative cos 2 pi on 6 plus c. Therefore, half is equal to, so cos 2 pi on 6, that's cos pi on 3. Cos of pi on 3 is equal to a half, so that's negative half plus c. Oh, that's boring. Oh, kind of. No, it's not really. Therefore, we can solve for c. If we move that negative half over to the other side, that will add half to that side, so c is equal to 1. Half plus a half, c is equal to 1. Therefore, my final function that we get, this in particular, if it goes through a point, f of x must be equal to negative cos 2x plus c, and c is equal to 1. So that is the function that it goes through. So in fact, it's funny that I actually put that dot on that black line, because it is actually that black line, because c is equal to 1. So the answer is actually that curve there, and at some point it must go through the point pi on 6 half. In fact, I reckon I've actually maybe even, no, it's not really that. But anyway, you get the idea. So that's what we're doing there. So that's what to do for families of curves. Let's just have a look at a different type where it's not really a family of curves question, but just something that probably doesn't fit somewhere else. Sketch a possible graph for y equals f of x given here. And so here we've been given a graph of f dashed of x, okay, so the derivative. So what might the original function look like? Let me just draw some axes, and then we can sort of have a bit of a play around. So let's have a think about it. Firstly, we know that there's an x-intercept at negative 3. What that means, the derivative is equal to 0 when x is equal to 3. Let me just write that down. X equals negative 3. We get, I'll just write dy dx. Might be a bit clearer. Dy dx is equal to 0. When the derivative equals 0, remember we get a turning point. So when x is equal to negative 3, at some point at negative 3, at some point when x equals negative 3, there's going to be some sort of turning point somewhere, all right? So I'll just get rid of all those dashes, but just to get an idea that at some point, and I'll just put a point in here, it doesn't matter. I'm just going to put a point in there somewhere. That's going to be a turning point, okay? Similarly, when x equals 2, when x equals 2, the derivative is equal to 0. And so that means there's going to be another turning point somewhere at x equals 2. So somewhere, and again, it doesn't really matter, but let's just put it there. All right, don't know. Another turning point there. Great, so we've got turning points, so 2 turning points. And so then let's have a look at the gradients. Here, in this area here, when x is less than negative 3, the gradient is positive. Okay, so the gradient is positive. So what that means is that beyond this turning point out here, oops, why was that not selecting? Out here, it's going to have a positive gradient. So it's going to be sort of coming up like that. Right, and then how about between negative 3 and 2? When x is between negative and 3 and 2, you're going to get a negative gradient because the gradient is below the x-axis here. You can have a negative gradient between there and there. And so it's going to sort of, I've drawn it actually pretty well. It's going to be coming down, so it's going to be sort of going downhill between those two graphs. Okay, so something like that. And then afterwards, after when x is greater than 2, you're going to get a positive gradient. So it's going to be sort of coming up like this. And so I'm thinking it's a cubic. The original function looks like a quadratic. And so that makes sense that the antiderivative of a quadratic will be a cubic. And so I think that the graph might look something like maximum, minimum, and then going up like that. So that's a possible graph. Again, it could be anywhere. It might look like this. It might be that and that. It could be like that. It could look like anything sort of like that, but it's a positive cubic coming up from there, definitely like that. But we don't know where exactly the turning points are, but that's a possible solution. It looks something like that. Okay, hope that makes sense. We'll see you in the next video.